Hello, and welcome to this technical presentation released to support our research into road surface integrity monitoring using millimeter wave radar for the IEEE Global Conference on Artificial Intelligence and the Internet of Things, held virtually and hosted in Dubai. I'm Jamie Blanche, and I am a research associate working for the Offshore Robotics for Certification of Assets Hub at Heriot-Watt University in Edinburgh in Scotland. Working in partnership with the Smart Systems Group and Microsense Technologies Limited, we are located at Heriot-Watt University's Riccarton campus. I am pleased to introduce our research, runtime analysis of road surface conditions using non-contact microwave sensing. To give a brief on this presentation structure, I shall start with an overview of the frequency modulated continuous wave system before outlining the technical challenge of highway asset integrity monitoring. This will link into our approach via the application of millimeter wave FMCW sensing and will lead into our experimental results, both in the laboratory and in the field, culminating with the sensor deployment on a salt dispersing vehicle. A summary of our observations will follow and a brief discussion of our future applications of the FMCW sensor in this role. Finally, I'll conclude this presentation with our author biographies and project contact details. For the sake of brevity, I will distill the FMCW theory section down to the statement that a millimeter wave frequency swept signal is emitted from the monostatic sensor, which receives the return signal and processes it as a comparison from the emitted signal. Analysis of the return data amplitudes provides insight into the properties of the material that reflected the incident wave. Of course, very few materials will reflect the incident wave in full, and the deconvolution of the return signal can be used to characterize certain material responses. For the fuller theory and sensor parameters, please do access our publications lists, which are cited in our conference paper. Our previous work with this method has determined a proven capability to detect polymer variations, features hidden by metal-doped paints, and low dielectric insulation layers, and features hidden within concrete, asphalt, and sandstone, all via non-contact operation. The system represents robust and tunable hardware with the potential for dielectric lens integration to determine radiation spot size on a target with tunable sensitivity through frequency sweep and sampling rate, and with multiple options for post-processing of the acquired data, either via real-time edge computing prior to telemetry or for later off-site data analysis during integration with digital twin architectures. Of course, using the data for predictive asset health makes operations and maintenance of an asset much more efficient and saves money via reductions in maintenance downtime. To continue the overview from the previous slide, FMCW analysis of a target provides previously inaccessible data on measurans indicative of failure modes in low dielectric materials and metallic surfaces, with the key advantages over other integrity monitoring techniques. The system is non-destructive and non-invasive, which reduces the risk by eliminating physical intervention and interaction. This means that the sensor can be used from a more remote or safe position with a usable range in the tens of meters. The data can be edge processed and communicated via telemetry in real-time or runtime. This is via handheld, vehicle, or robotic mounted deployment. The sensor is harsh environment capable, meaning the millimeter wave signal can return data in opaque environments, mist, dust, and in high temperature, high pressure settings, ultimately reducing downtime by operating in challenging conditions where optical systems fail. The system is reliable, with simple, robust, solid-state electronics designed to military specifications, meaning it can take a G-load shock having been ruggedized. The sensor is also ATEX CE certified, meaning it won't cause a spark in a flammable environment should it be placed in one. To provide an overview of the technical challenge for road asset integrity inspection, generally speaking, reducing operation and maintenance downtime results in greater asset productivity. Highways and byways are a major national infrastructural asset, and their smooth operation is critical to both the economy and the wider society. Reductions in highways efficiency therefore cost the economy and impact society. Our motivation is therefore to provide runtime holistic data of the highways network by providing edge analyzed data on road integrity via efficient salt deposition in wintry conditions. In doing so, we aim to optimize the resource expenditure of the valuable and polluting resource, salt, minimizing the environmental impact of salt dispersal on national road networks and the wider infrastructure it serves. Our method is that we have employed the novel application of frequency modulated continuous wave radar in the K-band for analysis of porous composite structures. We have approached this problem using our patented microwave sensing methods, which have been applied to several use cases. Although we are focused on road surface integrity here, our publications list and YouTube address, shown at the end of this presentation, showcase our parallel millimeter wave sensing applications. The common thread from all our research using this sensor has shown that the key advantages of FMCW result in a system with low power output with low demand on power systems, a non-contact and non-invasive sensor with an appreciable range, proven high sensitivity to salt, water, brine, oil, and porosity within low dielectric structures, and has a real runtime front-end analysis data capability and is suitable for low latency data telemetry with a roughly 30 millisecond computation time. FMCW sensing in real time can inform grid operations and private users of residual salt conditions and ice formation. Our work in this role stems from our applications to wheeled robotic platforms and, ultimately, is aimed at increasing confidence in braking systems at the time when you need them the most, in icy, wintry conditions. The value of this work is in the economic and bespoke use of salt under dynamic road and wintry weather conditions for optimal resource use for councils and to improve road user safety. Thus, our sensor system is intended for integration with vehicle systems and to augment currently available road monitoring systems, which are outlined in the published paper version of this presentation. Current guidelines issued by government institutions require predetermined dispersal volumes that are calculated as a function of road surface temperature and environmental conditions. These are, in turn, derived from weather station data and patrol vehicle observations. However, beyond meeting specific criteria, the presence of chemicals and salt products dispersed by council-operated or contracted vehicles is only quantifiable by the detection at very select and often sparsely distributed points. FMCW detection in the K-band offers a real-time and near-continuous road surface condition monitoring system with the potential to inform civil operators and private users of dynamic road conditions. By updating a synthetic environment architecture with this system, the state of health of the entire road network may be understood in runtime, while simultaneously adapting the salt dispersal rate to the conditions observed at the time. This saves the environment from excess salt pollution and optimizes resource expenditure. The FMCW signal response to 20% brown salt brine solution applied to a road section was evaluated at an ambient laboratory temperature. This figure shows the Fourier transformed amplitude extraction response in the time domain, extracted for the first interfacial reflector. Applications of 20% brown salt brine were deposited in the sensor field of view and allowed to fully evaporate before the same volume and concentration of brine was reapplied at the same spot in the sensor field of view. This was repeated 4 times to accumulate residual salt, and in each case the applied brine volume was equivalent to 30 milliliters per meter squared. Analysis of this figure shows the first application of 20% brown salt brine solution establishes a signal baseline, and with subsequent applications of the solution showing higher amplitude responses. The observed decay in signal response over time correlates to the water content in the brine solution evaporating, leaving residual salt levels incrementally higher than the previous application. From these results, it is established that the FMCW radar in the K-band is sensitive to deposited brine in the volumes used for de-icing roads. This next experiment tests the response to a melting layer of thin ice applied to a concrete slab which was frozen to -15 degrees centigrade prior to each application of salt or brine. So each applied layer was 1 centimeter thick over the 10 centimeter square target area and weighed 13 grams. Differing concentrations of salt were applied in 3 experimental runs. First, a control test used no added salt or brine and measured the time taken for the ice to melt and evaporate in ambient laboratory conditions. The second test applied an equivalent of 30 milliliters per meter squared of 20% marine salt brine to the 10 centimeter square test area. The third test applied 0.4 grams per 10 centimeter squared of rock marine salt. Observations show that the return signal amplitudes vary due to the ice melt, with a peak at maximum liquid water content and decreasing as the volume of water present in the field of view decreases due to the evaporation. The ice melt characteristics observed for each applied salt volume and type are detailed here, where point A represents the experiment start and salt brine added for non-baseline samples. Near immediate thawing for the rock salt sample is observed, and with the baseline thaw starting at approximately 2,375 seconds into the experiment duration. Point B represents the varying thaw transition rates from solid to liquid phases for all samples. Point C represents the liquid phase for each sample with varying return signals for salt content versus the baseline. And point D shows the liquid to gas evaporation phase resulting in the return response for residual salt volumes in the sensor field of view. Summarizing these laboratory tests, variations in salt type and concentration and their effects on ice thaw are detectable on representative road surfaces, again demonstrating FMCW sensitivity to distinct amplitude variations for differing brine and rock salt volumes. For field testing of salt present detection on an active roadway, we applied the FMCW radar to corroborate the results previously attained in the laboratory. How would the system fare in a real-world deployment role? Working with Tayside Contracts Limited, a contractor situated in Dundee, charged with the winter maintenance of the Tayside highways, the FMCW sensor was fitted to a fleet gritter vehicle for deployment on a standard de-icing route. This route covered approximately 13 miles and at an average vehicle speed of 28 miles per hour. These tests were conducted during cold but non-wintry conditions to minimize disruption to normal fleet operations. Each trial was performed at night to minimize variations in route's duration due to traffic and consistently disperse the minimum volume of salt from the salt dispersing system, which was 10 grams per meter square. This was for resource economy. As in the laboratory tests, the deployed sensor acquired data once per 5 seconds. The sensor was mounted 1.7 meters above ground level, giving a field of view of approximately 1.2 meters squared of the moving road surface. Results acquired are shown, with 3 laps of the route driven consecutively, where an increase in return signal amplitude for each trial is observed in the data median for each lap of the route, indicating that K-band FMCW is sensitive to the deposition of rock salt on the road surface, despite the presence of a significant noise floor. Data obtained from a weather station located on the test route gives the conditions on the night of the experiment as consistent throughout the test period, with no rainfall and a measured surface temperature ranging between 7 and 8 degrees centigrade. This data shows that laboratory-based and field experimental results are consistent and validate the suitability of K-band FMCW sensing in this role. Understanding the condition of roads and highways in winter conditions is crucial to the efficient operation of national transport networks. Treatment of road surfaces under present guidelines requires the deposition of set salt volumes per unit area and is assessed by measured local temperatures and forecasts. The accurate and real-time measurement of residual salt volume on the road surface is not currently applied to protocols that define the volume of salt to be deposited. Our results demonstrate that FMCW sensing, readily deployable on road vehicles, provides a means of accurately monitoring actual road surface conditions via a signal parameter tunable, non-contact and non-invasive method. allowing for data aggregation via real-time or runtime data telemetry and transmission to live infrastructure databases and digital twin systems via the Internet of Things. Our goal, therefore, is to integrate the live road integrity data onto a salt dispersing vehicle for real-time resource optimization, resulting in the bespoke dispersal of salt and the intelligent sharing of highways integrity data for real-time transmission to the highways authorities. This research has demonstrated that FMCW sensing can provide access to previously inaccessible road surface characteristics as shown from our laboratory and field trial analyses. Measurement of FMCW return signal amplitudes has evaluated residual salt volumes per unit area against a known baseline. These experiments have also shown that ice and ice melt are distinguishable with unique FMCW signatures in a laboratory environment. Field deployments had verified the capability of FMCW to detect residual salt presence from previous depositions and allows for the runtime assessment of road surface salt volume on a moving vehicle. In future work, the developed FMCW sensor system will be complemented with software programs that collect, view, and manage data automatically via machine learning. Our data can also be integrated into a holistic infrastructure and asset integrity model, with real-time sensing incorporated into a digital twin model for the human-in-the-loop decision-making, allowing for the optimization of salt-dispersing vehicles and resource expenditure. The measured data can also be sent to road maintenance engineers in real time to perform road maintenance operations that are specific to an assessed geographic position. Further development will assess the potential to detect porosity and delamination between asphalt layers, water and ice ingress, and detect subsurface delamination and precursors to pothole formation via the continued deployment on a private research vehicle. While you are at this conference, I invite you to view a presentation by my colleague, Mr. Leo Kong, titled Interactive Digital Twins Framework for Asset Management Through Internet. Leo's work details where digitalization influences design, operation, and management, as well as planning functions for products and services across a myriad of industries, and where the results of the applied digital twin are demonstrated using embedded front-end sensing for offshore energy assets. If you are interested in a system that can filter and translate complex data and messages from any embedded sensor and operating system, Leo's work is well worth your consideration. You can also visit our YouTube channel, Smart Systems Group, or Orca Hub websites to view our latest research presentations, public outreach, and news features. Simply search for Smart Systems Group, Heriot-Watt University, or Orca Hub in the YouTube search bar or Google, or follow the web addresses above. Thank you for watching this presentation. Please feel free to reach out to us online, and we look forward to future engagements.